prezentarea. Hello, so today we're going to discuss about some architectural designs of neural networks, about the training algorithm for neural networks, which is backpropagation. So the plan for today is to discuss the notation and the setup, to present some basic neural network architectures, and to present the chain rule and the gradient descent algorithm and the backpropagation process. So I know that some part of this we already discussed in the practical machine learning, so some parts are new, but overall the main objective is to at least have a recap of the last year and fix the information for the next slides. Okay, so we start in the supervised learning paradigm, where we have an input X, an output Y. So these are associated labels to the input examples. So these are the examples are from a high dimensional space, and there is a function which is unknown that maps the samples from X to Y. So this function is actually a continuous function. So in theory, at least, we have a mapping from every possible sample in this domain X to the corresponding target. But in practice, we have some set of discrete observations from this space. So we will try to approximate this function, this continuous function, with a function considering the available data that we have. So the first, let's say the first step in addressing this problem, in trying to find the function f, is to define a model or a hypothesis class. So in some examples we can use linear models, but in neural networks we will use more complex hypothesis class. So this means that the form of the function g that we learn through that we learn from the data can have a complex form. So it can be composed of multiple functions. So as we discussed last week, the function g in neural networks is about composing different functions and obtaining a complex function that is able to model all the complexities of the function f. Okay, so essentially what we do when we define this hypothesis class, actually in neural networks, we define the architecture. So if we use, for example, a neural network with 2 layers, we have a simpler function. If we use a neural network, I don't know, with 10 layers, we have a significantly more complex function. So it really depends on the architecture that we use and the activation functions and so on. And also, once we have the architecture, we try to find the weights that optimize some loss function, and this is done using backpropagation. Okay, so now back to the basic steps of supervised learning that also apply to deep neural networks. So first we need to set up the supervised learning problem. So usually we have to do data collection. This is either done by us, so we have to go and collect data and label and so on, or sometimes we might find already data that's available and just use it for training. Then there are 2 steps: the representation, which so let's say the raw data could be images, audio files, video clips, I don't know, text documents, and so on. Can be any kind of raw data. that you might want to classify, and from this data you want to obtain a representation. Okay, so this representation and is actually built in the learning phase. So essentially we can couple together the representation and the learning part in a single step, and we call this end-to-end learning. So in traditional supervised learning, these are independent steps, and we have to define the representation, then choose the modeling hypothesis, and then we do the learning. But here in deep learning, the representation step and learning phase are jointly done together. Okay, so in the learning, of course, we can try to optimize different models with maybe based on different hypotheses. And in the end, we choose the model that has the optimal performance. And if we're happy with its performance, we can stop. Otherwise, we can go back and try to, I don't know, find better ways to optimize the model or to choose another hypothesis class and so on. Okay, so we discussed now in the learning process, we discussed about a loss function, and we also discussed this last year. So usually when we try to estimate that target function that is continuous and unknown, usually we have an error of the estimation, and this error can be decomposed in different things. So essentially, we have the reality, the points, the data points that we have from a space X, and the corresponding labels. So in this example, we just have an image and some segmentation maps associated to the image. And we propose a neural network architecture that represents our model class. So usually this model class doesn't match the reality perfectly. Actually the reality is can be modeled with very complex functions, and since we don't have all the training data available, this is unknown, and when we choose a model class, it will not model the reality. So the best we can do with our model class would be a point that gets as close as possible to the reality, and we call this error the modeling error. Okay, so essentially, if we want to reduce the modeling error, we just try to use more complex neural networks. So usually deeper networks provides, using deeper models, usually provides better performance. But there is also a question of the number of training examples. So if you don't have enough examples, the model might overfit, and you will not get good results. Because there is also other types of error. There are also other types of errors, like the estimation error and the optimization error. So the estimation error is the error that is caused by the learning process, and also the optimization error is caused by the optimization algorithm. So for example, in deep neural networks, the loss function is a non-convex function, and you might end up in a local minima, or you might not optimize until the minimum point. So in this case, you get an optimization error. Okay, so usually if you, based on, as I said before, based on your model class, so if you choose a simpler model, I don't know, like a linear model such as SVM or logistic regression, you will be able to minimize the optimization error and the estimation error, but you will implicitly increase the modeling error. If you increase your model class, you will reduce the modeling error, but the optimization and the estimation errors might increase. So it's usually a trade-off between two, and actually adjusting, I think, the model class to the data set gives you the best performance, but you still have to try different architectures and see what works best for your data set. Okay, so now we start discussing about neural network architectures. So the the basic unit that we use to build neural networks is an artificial model of the biological neuron. So in biology, neurons have different components like the dendrites that receive electrical signals as input. These are accumulated in the cell body, and the cell has a certain threshold. So if the electricity passes this threshold, then the neuron gets activated and passes the signal through the axon, which communicates with other neurons. So the first model of the neuron, the Rosenblatt neuron. So Rosenblatt proposed a mathematical model of artificial neuron to model these biological actions that happen in the brain. So the dendrites are modeled by some inputs, and the strength of the synapses that connect the dendrites to other axons are modeled by some vector of weights. We have the cell body, which accumulates the information. So this mathematical notation, this means that we calculate a sum, and then we apply an activation function or a transfer function. So if this sum gets higher than a threshold, usually it should activate the neuron and pass on the information. Okay, so there are several types of neurons which depend on the activation function. So the one defined by Rosenblatt is called the perceptron, and this one has a sign activation function. But we also have logistic neurons, which are used in neural networks or were introduced in order to be able to train neural networks with gradient descent, which require functions that are continuous and have some gradients. So for example, the sine function is not neither derivable, and neither when you compute the gradient on the constant 1, the gradient is 0, and you cannot update the model based on gradient descent. Anyway, so these are some types of neurons. Of course, there are newer models that use rectified linear units and other modern activation functions. So these are just some basic neurons. Okay, so we also have in terms of the activations. So historically, we have the sigmoid and the hyperbolic tangent. And the problem with these two, so even if they are continuous and we have gradients for them, and we can optimize neural networks with these two functions, the problem is that they saturate towards plus minus infinity. So it means that when we try to compute the gradient of this function, which is almost constant here, it means that, so since the function is almost constant, the gradient is almost 0. So when you try to do gradient descent, the update is almost 0, so you cannot actually update the network. Okay, and also another problem is that the sigmoid has non-zero mean, and this might cause problems if your data is not centered, and so if it's not standardized, you might have optimization problems. And anyway, in 2012, Alex Grzewski trained their AlexNet model that was used to participate in the ImageNet challenge. They successfully used a different type of activation function called rectified linear units. So this function is just the maximum of 0 and x. So they found that the training time is much smaller using ReLU compared to I don't know, sigmoid or the hyperbolic tangent. So the network converges much faster if you use this type of neural units. Okay, so so far we discussed about individual neurons. So if you recall from last year, a single neuron provides a linear decision boundary. So essentially, it creates a hyperplane that divides the space in half. So it's a simple linear model. So in order to build more complex models, the idea is to stack them together into neural networks. So this is how we develop multi-layer perceptrons or multi-layer neural networks. So we have the neurons organized into different layers, and the information is typically passed from a previous layer to the current layer, which passes the information to the next layer, and so on. So these are just two examples with a neural network with one hidden layer and a neural network with two hidden layers, and you see always the information passes from one direction to the other. Okay, so yeah, as I said before, each layer has its own set of weights. So actually each neural unit has a set of weights, and the purpose of training the network is to try to find the weights that optimize our loss function. And again, if we go back to the biological meaning of this, we are trying to build the connections between neurons, so the strength of the synapses between neurons, such that we design some sort of a small brain that is able to take some input and provide the right input. So we're trying to train the small brain to perform a certain task. Okay, so now we have different, the networks can have a different number of layers. So for example, for a network with two layers, we can also write it. So this is the graphical notation of the neural network, but we can also use matrix notation to define the computations that happen in the neural network. So for example, for a two-layer neural network, we can define a generic function that has this form. So we have the input x is multiplied with a matrix of weights. So this matrix contains all the weights going from the input to every neuron in the first hidden layer. Okay, so then we apply some transfer function. So in this case, we use the ReLU transfer function, which is max of 0 and the input. And then this we multiply with the weights from the second layer and so on. So this is a two-layer neural network. For a three-layer neural network, we have an even more complex function that takes this form, and so on. So looking a bit at the details, yeah, so for example, for the input and a hidden layer with 4 neurons, and an input of 3 of size 3, we have a matrix that has 3 by 4 weights. So in total we have 12 weights that we want to optimize on this layer. Of course, we also have the bias terms. So this shifts the position where the neuron activates. So these provide some output, and here we have a single neuron unit. So actually the matrix is just a column vector in this case. Okay, so this is the basic design of a neural network architecture with feed forward information. In our lectures, we will also discuss about more complex architectures that can also pass the information back to the input. So these are called recurrent neural networks, but we're not going to discuss about them until lecture 6 or 7, I think. Okay, so yeah, what we do here is stack together a bunch of neurons, but one key important aspect here is to make sure that we have transfer functions that are nonlinear. So essentially, if we go back to the neuron, so we can also, as I said, we also have this type of neuron which is has a linear transfer function. So it means that the transfer function is the identity function. So f of x is equal to x. So in this case, if we go to, let's say, to this equation here, and we replace this with f of x is equal to x, it means that the function corresponding to a two-layer neural networks will be w2 multiplied with w1 multiplied with x. So essentially we will have no transfer function here. Okay, so in this case we can also multiply w2 with w1. So we can do so. Yeah, we will have this matrix multiplied with this matrix and multiplied with this vector. But what we can do is actually we can also multiply. So usually when we perform the computation, we multiply x with w1 and then we multiply the result with w2. But since we will not have the activation function, then we can also multiply w2 with w1. So for example, in this case, let's say, so this is w1 and this is w2. So when we do the multiplication, then we will obtain a matrix of 1 by 3, and then we multiply this with x. So this means that actually the two-layer neural network, when we multiply the weights and obtain a single column vector of weights, will be equivalent to a linear model, to a single neuron. So the nonlinearity is very important here to ensure that your model is a complex function and is not a linear one. Yeah, so the main conclusion, so usually I would have done this proof on the checkboard, but since we're using online, yeah, I'm trying to explain using the slides from before. So this will also happen with even more complex functions. So if we remove the transfer functions and we have just w3 multiplied with w2 and multiplied with w1, then we can also do the multiplications from the left to right, and in the end we will have a single vector of weights. So this means that the three-layer neural network is equivalent with a linear model. Okay, so yeah, this is not what we want. So the nonlinearities are very important to ensure that we have complex function. Okay, so then we have this important theoretical result, which says that neural networks that have at least 2 layers, so this means that the function has to be non-linear. Okay, so it's a function that it is at least as complex as this one shown here. Okay, so going back, yeah, a 2-layer neural network with linear outputs can uniformly approximate any continuous function. So this means that you can learn, you can approximate. So recall that what we want to do here is to approximate an unknown function, unknown and continuous function f, right? So yeah, we have a continuous function that maps x to y. So we have this theorem that the neural networks with at least 2 layers can approximate this function on a finite subset, right? So this is a small constraint, but it's still not very problematic. So finite subset means like Cartesian product of intervals in this big space of your input data. So if x is, for example, the Euclidean space R to the power of n, then yeah, you will just need a subset of this space, and you can model this continuous function that you want to obtain in this subset. So yeah, this is not such a complicated thing. So essentially, you can, if you can normalize your data points, for example, I don't know, using the L1 norm or using standardization. So all your points, for example, will be in the cube minus 1, 1. Then that's your finite subset. So you'll be able to model this complex function on your finite subset. Okay, so this is what happens in theory. The only problem with this is that we have no boundary on the number of hidden units. So essentially, if you have very complex functions that you want to approximate, you will have to use many hidden neurons on your 2-layer neural network. So the main result of deep learning is that, and this is I think this is actually proven, that the network, as it becomes deeper, it needs less hidden units in order to approximate this continuous function. So instead of so for example, for complex problems like, I don't know, image object recognition in images, I think the number of units is for a two-layer neural network is exponential with respect to the number of inputs. So yeah, if you want to use a manageable number of units, you will need to use deeper neural networks that can model a more complex function. Okay, so yeah, this is the theoretical result. So essentially what we get out from this is that with a neural network, we can make sure that it can learn the entire trained data. So it can overfit to any classification problem. So this is this means that the model is very strong, and it has the hypothesis class is very large, but it could also the drawback is that it could also go into overfitting. So you might train the network and performs such that it performs with 100% accuracy on the training data, but you will get I don't know, very bad performance on your test data. Yeah, so it means we have some strong tools, but we need to learn how to use them in order to obtain the desired results. Okay, so now discussing a bit about the recap from last year. So when we want to discuss about gradient descent, so essentially we start with some loss function that we want to optimize. So in the last layer, so this is also um, some linear model, SVM and logistic regression, but these can also be used in the last layer in a neural network. So usually this is called the classification layer, and depending on the loss that we use, if we use the hinge loss, which is based essentially on minimizing the norm of the vector of weights and the margin with respect to the wrong classification of an example. So essentially, the hinge loss looks something like this. So yeah, what it means is that, so if you're predicting the correct class here, it means that the loss is 0. So this term here becomes negative, and maximum of 0 on something negative is 0. So the loss is 0. So once you classified an example correctly, the loss becomes 0. So that's fine with the SVM. And if it's not classified correctly, then the loss is higher, and you will have to optimize the loss in order to make sure that the example is classified correctly. Okay, so yeah, this is the hinge loss. And we also have the log loss, which seems to work usually better than the hinge loss. So this transforms the loss function into, let's say, into a more derivative function, but it's not actually about the derivative. It's just about that it makes a more smooth. I was looking for this word. So it's a smoother loss function. So the thing is, even if the example is classified correctly, if the difference with respect to the other classes is not large, you will still have a significant loss that you need to optimize. So essentially, if you predict the probabilities, let's say 0, 4, 0, 3, and 0, 3, so 0, 4 is for the correct class, so you get the right class, but still the probability is not that big in comparison to the probabilities predicted by our model for the other classes which are wrong. So in this case, you still want to optimize the model such that it will be able to predict the probability, I don't know, 0.999 or something like that for the correct class, and the probability is 0 for the other classes. Okay, so the logistic regression loss, also known as softmax or log loss, has this form. So you still want to minimize the vector of weights, but you the second term is to optimize the minus log likelihood of the example X to be classified into the correct class Y. Okay, so moving forward, essentially the loss function. So we discussed about individual losses for an example X. So for every example, we have, I don't know, a different loss function, and in the end, when you optimize the sum of all the losses with respect to every data sample. So yeah, the sum here means that you will get a loss function that looks something like that. And in the end, for a linear model, the problem is convex. So if you start with some weight, so yeah, remember that this graph is on the horizontal axis you have the model, so these are the weights, and on this axis you have the value of the loss. So the same thing here. So now going back to the SVM loss, so let's say we have three training examples. So two should be I don't know, positively labeled, and one should be, actually I think it's the vice versa. So one that is positively labeled and two that should be negatively labeled, and they have I don't know, different margins. So you have, for each example, you have this a loss function like the green one, the red one, or the blue one. And when you optimize actually the sum of these loss functions. So the sum is just actually the highest part in this case of these functions. So here, if you make a sum, it should be a bit more steeper, as you see here. So the function is a bit steeper than these two because you just compute a sum. So anyway, so in this axis we have the weights W, and on this axis we have the loss. And in the end, when you compute the sum, you usually so it is proven in theory that the resulted loss function is a convex function, so which means that you can optimize it with gradient descent. So convex, it means that it has a minimum in a single location, so it doesn't have like I don't know, mountains or other shapes like that. Okay, so we mentioned about gradient descent, so we're going to make a short detour about gradients and what gradient descent is. So essentially, as I said previously, in linear models, the loss function is a convex one, and usually you can apply gradient descent. Of course, this is one option. There are also other optimization algorithms, but you can apply gradient descent to optimize. So you start from a certain location, you try to compute the gradient of your loss function in that respective location. So the gradient gives you the direction, actually the negative direction of the gradient is the direction in which the function decreases. So you follow this this path until you find the local minimum point. So since we're optimizing convex function, there will be a single minimum, and that is also the global minimum. So you'll find your optimal model in the end. Well, the problem with neural networks, if you go to more complex function, to nonlinear functions, then the loss becomes non-convex, so it can have just like a relief. If you go to the mountains and see how the mountains look, you will see it has different points of minimum, different points of maximum, and so on. So yeah, in the end, you want to find the global minimum in this space, and of course, it's not easy to traverse it or to find the minimum. So one possible solution is just to use gradient descent. So this was mainly one of the main tools that they had to train neural networks, and well, it seems to work. So even if the loss function is non-convex and we're not using the right tool in order to optimize the model, it's still a good enough algorithm to obtain good results in practice. So of course there are ways to avoid local minima using gradient descent. So one option is to use mini batches and so on. So we'll discuss about these in a few moments. So yeah, now I think I have so a few slides that are more of a recap from last year, but I think these are important to remember in order to discuss about future things that we want to discuss. Okay, so in order to apply the gradient descent algorithm, we have to compute the gradient of our loss function with respect to the variables that we have. So this is just a notation for a one dimension. Of course, even a linear model has more variables than this. So we have an entire vector of weights, and also the loss also depends on the input. So actually the function, um, the input of the function is not only some variable x, but is actually the whole training data set x and the weights. So imagine that for a neural network, this becomes even more complex since we have more weights. Okay, so anyway, in general, in multiple dimensions, the gradient is a vector of partial derivatives, and this can be computed on each component individually. So once again, if this would be a physical class, I would draw some things on the table and show you how gradient descent works. But instead here I will just use some slides, and also we'll try to look at some code and analyze the code, and hopefully you'll figure out from the slides and from the code how the algorithm works. Okay, so yeah, one way to apply the algorithm is to apply this formula from the previous slide, which is the numerical form. So if you have to know the analytical form of the derivative of the function, or you can compute it numerically. So you just take a very small constant value h. You compute the function in this location, and you just subtract the value of the function in this slightly shifted location with respect to the current location, and this gives you the value of the gradient. So this is what we're doing here. We're trying to optimize the weights w. So in order to to optimize, for example, the first component, as I said, we can apply this on every component individually. We update the weight with a very small positive constant. We compute the new loss value, so we obtain this value of the function. This is the old value, and now we apply the formula from the previous slide. So yeah, the value of the loss function when we slightly updated the weights, so we shifted the location, we obtain this value, we subtract it, we subtract the initial value, and we divide it by h, so we obtain the value minus 2.5, and this is a good approximation of the gradient in this location. So we can do this for every component in W. So here, once again, we update with a small positive constant. We obtain a different loss value. We compute the difference, divide it by the step h. We obtain an approximation for the gradient, and so on. So we do this for the entire vector, and once we have the gradient, we can apply the gradient descent algorithm. We're going to discuss about this in the next few slides. So yeah, so far we have discussed about the numerical approximation approach, which involves the computation of the function f in this location x, and for each component that we optimize, we have to recompute the function in the respective location. So if you have a single variable, this means that we have to compute this function twice. If we have, I don't know, a vector of weights n, we have to compute the function n times. So imagine if you have a large number of weights, then it will need we will need to make a lot of forward passes through the network in order to compute the values of these functions and be able to compute the gradients. So this is very slow to compute in practice, and we usually prefer to use the analytical approach. But here you will need to use either to use some knowledge of calculus, or you will need to use a framework, for example TensorFlow or PyTorch, that can compute the gradient for you, at least for predefined functions. So I think that in TensorFlow 2.0 you can essentially use any function that you want, any architecture that you want in your neural network without worrying about computing the gradients and so on. So that's very, very convenient. Anyway, so in the end, we compute the gradient with respect to every component in W, either using the numerical form or the analytical form. So we obtain the gradient, and then we apply the gradient descent formula, which is the previous weights are updated in the negative direction of the gradient. So this is the gradient of the function f, and we updated the weights, so the weights here are updated in the negative direction of the gradient. And here we also use a certain step function to a certain learning rate in order to update the weights. So it could be one problem of the algorithm could be that if the function is very steep, the gradient will be very large in a specific location, and it can take the direction, take a big step in the direction of the gradient, but since it might be the step might be too large, it might not be optimal. Okay, so yeah, as I said, we have some code in Python that we can look on and analyze a bit, and actually recall from last year how what's the meaning of the gradient and how we can implement the gradient descent algorithm actually from scratch. So here, as a toy example, we're trying to optimize a function f that has a polynomial shape. So the function is 0.5x to the power of 4 minus 2x to the power of 2 plus x plus 5. So yeah, we can either compute the numerical gradient using the definition from our first slide on gradient descent, or using the analytical method. So of course, for a polynomial, I think it's not so complicated to compute the derivative. So here the derivative of this function, so what happens is that the power drops by 1 and we move the current power in front. So for the derivative, we obtain this polynomial function, so 2 times x to the power of 3 minus 4 times x plus 1, and of course the constant becomes 0. Okay, so we can either compute the gradient like this or like this, and then we apply the gradient descent algorithm. So the update rule, as I described in the previous slide, is updating the weights in the negative direction of the gradient. So we subtract the gradient and we multiply the gradient with sub-unitary constant, which is called the learning rate, to make sure that our update steps are not that large. Okay, and now one stopping criterion for the algorithm could be the number of steps that we perform the update, or it could be the difference from the current W to the previous W. So since this update gets smaller and smaller once we reach a plateau. So if we reach a plateau, then gradient descent, the gradient becomes close to zero, and the update will be very, very small. So if we reach a plateau, the algorithm has almost reached the local minimum, so we can stop the algorithm. It should be very close to the minimum. Okay, so yeah, just before discussing about this slide, I'm going to discuss about to discuss about a practical example with gradient descent, and actually also we're going to discuss about gradient descent with momentum. So this is just from the example from the slides that I showed you before, exact same function and the same derivative. Yeah, so when I run this code, you will get this graph here. So you see that we start. So on this axis we have the value of x. So we start from the value 2.5. This is the initial value. So usually in neural networks, we start with some random initialization of the weights, and then we try to perform gradient descent, with respect, so starting from this location. Okay, so we also have the learning rate, which is 0.01. So you see it has a small step here, and yeah, so about just one moment, just to figure out what are the colors. So yeah, the blue function is the function that we want to optimize, and the green function is the gradient. So why does gradient descent work? Because it indicates where our function decreases or increases. So based on the sign of the gradient. Okay, so what this means is that, for example, the gradient, for example, in this region is negative. So this is the intersection with the horizontal axis. So what's below this axis, the gradient is negative. So where we see a negative gradient, it means that our function going from left to right is decreasing. So here the function is decreasing. Here, when we have the gradient equal to 0, the function has is constant. So here we have a plateau, and then from this point it starts to increase. So the function, our function in blue, starts to increase until this point. So this is where the gradient is still positive, so it's still increasing. So here we has another plateau, and this is a local maximum, and then it starts to decrease slightly until this local minimum, and then it starts to increase again, which means that the derivative is positive. Okay, so for example, in this location, from left to right, our function is, so this is the direction of the axis, right? So if you go right, x will be higher, and if you go left, x will be smaller. So in this location, if the function increases in this direction and we want to minimize it, we should go in the negative direction of the gradient. So here the gradient is positive, and if we make steps in the negative direction of the gradient, we will make steps in this direction. And also I mentioned that the magnitude of the gradient is important. So as you see, is here the gradient is closely approaching 0. So this means that our updates are smaller and smaller. So as I said before, this means that we have so small updates. It means that the algorithm is very close to the global minimum, and we can stop the optimization there. Okay, so we can also try to see what happens if we increase the learning rate. Let's try, I don't know, 0.1. Yeah, so here I'm not sure where it stops, but so it started from here and it made an update, I think until this point, and then it started to slowly decrease back to this point. So it still performed okay, but if we increase it even more, then probably the behavior will not be yeah, sorry, so this goes, I think, beyond my graph. This also, let's try 0.2. So this is also displayable. Yeah, so in this case, you can see that the update from here, I think, went probably to this point and then to this point, and it started to optimize in this location. So yeah, in this case, we, instead of optimizing towards our with our slope towards the local minimum here, we made a very big jump to a different location, and now the algorithm is less predictable. So the learning rate, it is important not to have a very big learning rate, because we can end up in situations like this. And yeah, in the previous example, we had a lucky example. So we escaped this local minimum and we reached the global minimum here, but actually also the reverse can happen. So if we start in this location, which is close to the global minimum, and we make a very large update in the negative direction of the gradient, the update will be somewhere here, and then the algorithm will converge to this local minimum, and we avoided the optimal solution. So if we choose the right learning rate, then the algorithm is more stable and behaves as we would expect it to behave. Okay, so this is the gradient descent algorithm. So also a brief recap about the gradient descent with momentum. Let me just quit this and run. Let me see. So the code is gdm.py. Okay, so this is essentially the same function that we just apply gradient descent on top of it, and actually can also see in this figure an animation of how the optimization occurs. So after it stops, I'm going to restart it and try to watch from the beginning. So I think it starts from a location somewhere here, and then it optimizes to this minimum. Yeah, so in gradient descent with momentum, we also have this additional term, which takes the difference from the previous two updates and multiplies it with a momentum rate, usually denoted by mu. So this actually behaves more like a ball going down a surface and catching some momentum, So because of this momentum, it can escape. So because of the inertia, it can escape the local minimum. So it starts from here, and it goes. It escapes it escapes the local minimum, and it goes here to the global minimum. Okay, so yeah, this is how gradient descent with momentum works, and of course there are other algorithms, and even the standard gradient descent can have can escape local minima solutions if we use mini batch training. So what's the main problem with gradient descent is that for large network it requires to compute a lot of gradients. So imagine computing the gradient with respect to every input x and every weight. So essentially we have to compute very large matrices. So in order to avoid these large computations of gradients, the idea is to train the algorithm on smaller batches of data samples. So in practice, we usually take, I don't know, 16, 32, 64, and so on. So we try to use mini batches of examples instead of the entire training data set. And so this is this helps us to reduce the computation, but also it transforms the gradient descent algorithm into a stochastic approach, which means that it introduces some randomness in the process. So for example, if you try to optimize the loss function with respect to a mini batch of examples x that is quite small, I don't know, with respect to the entire training data that can have thousands or millions of examples, you're actually optimizing an approximation of the loss function, and this approximation, for example, can have a gradient that's not really perfectly correlated to the gradient of the loss function when you consider all the training data points. So this introduces some randomness in the training process, and then when you optimize, actually your steps become a bit more random, and because of this you can also escape local minima. So yeah, you can imagine that. So you have this loss function like the ground truth, and then when you compute the loss function for some mini batch, you get a slightly different shape, and for another mini batch you get a slightly different shape, and so on. So in the end, if you want to imagine this, it's like you would take this ball, as in gradient descent with momentum, and try to roll it down a carpet and find where it stops. It will be the local minima. But now instead, when you use gradient descent, you also shake the carpet, so it the shape of the function will not be always the same. It will not be constant. It will have this slight random perturbations that makes actually, if you imagine this shaking and the ball going down and having some local minima and so on, because of the shaking you can pass this local minima. Okay, so yeah, and this is just an analogy that I like to make and to imagine the training process. So essentially, the advantage is that we have less computation with stochastic gradient descent based on mini batch, and also it can escape local minima and converge probably to better solutions. Okay, so now going back to the training process in neural networks. So we just discussed about linear functions and so on. So in order to be able to update neural networks, we We try to take advantage of the compositionality of the network. So for example, we can also represent logistic regression as a composition of different functions. So here we have a linear model, like a linear unit, right? So we have some weights that we multiply the input with, and we get the output u. Then we apply the transfer function, the sigmoid, which is 1 divided by 1 plus e to the power of minus u, and this results in p, and then we apply the minus logarithm on p, and we get the loss function. So in order to optimize this composition of functions, we apply the chain rule. So essentially this is applied on each component in our neural network. So let's say we have some unit that has an input x and an output y. When we compute the gradients, we have the gradient of the loss function with respect to the output. So we assume that this is computed until this point. And yeah, in order to compute the output gradient with respect to the input, we apply the chain rule. So this is the chain rule. So in order to pass the gradient through this unit, we have to multiply the gradient that's going backward into this into the current unit with the local gradient of the function. So the local gradient, so the function is y, so the gradient of y with respect to x. So this is the gradient of y with respect to x. We multiply it with this gradient, and we obtain the gradient that can be used to update the rest of the network. So these are just some components in a large neural network, and we use this rule on each component in order to update the entire network. So going back to the logistic regression as a cascade, so here we have the gradient of the loss function with respect to p. So for this unit, the gradient, the gradient is, for the logarithm, the gradient is 1 divided by x. So the minus logarithm is minus 1 divided by p in this case. Okay, then the gradient, we have the gradient of the sigmoid function, and the gradient of this function is the value of the function multiplied by 1 minus the respective value. So it's p multiplied with 1 minus p. So this is the local gradient. And also here in the end we have to optimize the weights w of our model. So in order to compute the loss of the loss function with respect to w, we take the loss with respect to p, multiply it with the loss of p with respect to u. So u is the input here and p is the output from this unit. And then applying the chain rule one more time, we multiply it with the gradient of u with respect to w. So yeah, in the end, here the gradient of u with respect to w, so if we have w multiplied by x, the gradient, when we compute with respect to w, the gradient will be x. So here we have an x, and here we have p minus 1, because here we reduced the p from this component with the p from here, and we used minus 1 to reverse the term here. So minus p is p, and minus 1 is here. So in the end we have this value of the gradient for the weights in logistic regression. So then we can update the weights according to this model. Okay, so the computation in the training, we have two steps in backpropagation. So backpropagation is actually based on computing the gradients of the loss function with respect to the output, and then propagating these gradients through the entire model until we compute the gradients with respect to the weights, so we can update the weights in each layer of the network. So yeah, we have the forward pass in the model, so we have some input x and some output in a certain unit, and here we use some weights denoted by theta. And then in the backward pass we have the local gradient, which is usually computed with respect to x and with respect to the weights, and also the gradient it comes into this unit. So here actually the unit has some weights, and in order to update the weights we have to compute the loss with respect to the weights of this unit. But also if imagine that the input of this unit comes from a different neural unit, and that neural unit also has some weights. So in order to be able to update those weights, we also have to compute the gradient with respect to the input of the current unit, so that we pass the gradient to the previous unit, and that unit will be able to also update its weights. So that's the backward pass. So in the end, the training is composed of doing the forward pass through the network, which for a mini batch is usually done only once. So we do the forward pass, so the information passes from the first layer to the second one and to the third one and so on. And then we do the backward pass, in which we compute the gradients and apply the chain rule. And after we computed the gradients for all the weights in our neural network, we just apply the gradient update rule. So this is the basic rule of stochastic gradient descent, but we can, as I said before, it can have different forms and additional terms, like in gradient descent with momentum. We also had the momentum component. Okay, so here we have the weights denoted by theta, and the learning rate denoted by nu. So these are just, and this is just a notation for the gradient. So essentially the update rule is the same as presented before. Okay, and yeah, this is the variant with momentum. Okay, yeah, so I wanted also to emphasize that we're going in the negative direction of the gradient. So this is important. So if we look this into a two-dimensional space and we compute the gradient with each component, so here we have W1, and on this direction, on the horizontal axis, we see that the function, the negative direction of the gradient is in this direction. With respect to the other dimension, we have the negative direction in going upwards. So now if we compose these two components of the gradient into a single vector, we obtain this gradient vector, and this is the update that we are going to make. Okay, so yeah, this is the gradient descent algorithm. Yeah, here we have some different notations for the components in neural networks. So you will see, I don't know, in other lectures or other books or materials, you will see different notations actually meaning the same thing. So yeah, this is kind of the expanded form, and here it's more based on the mathematical equations and so on, but essentially it's the same thing. Okay, so we are close to the end. So I have some questions for you to answer. So I would like you to see the answer. So the first question is, do you think backprop works only with sigmoid activations or other functions? So yeah, as I mentioned earlier, um, we cannot apply it with the sine function because we have no gradients, and we had to replace it with the sigmoid. Okay, so yeah, the question is actually what activation functions we can use. So what's the, let's say, the mathematical constraints for the activation functions to be able to train backpropagation. Okay, so this is the first question. I have the answer written down, so I cannot pass to the next question before I see an answer from you. Okay, so we have an answer which is not correct. So it doesn't work with any activation function. As I said before, it doesn't apply to the sine function because the gradients will be 0 and you cannot update the model. I'm not sure if I understand. Perhaps you can write in Romanian. Okay, we have a good answer. So yeah, it has to be almost everywhere differentiable. Okay, so yeah, this is a good answer. So what this means, for example, the ReLU function is differentiable in almost every point besides 0. So as I said before, neural networks can be optimized if we have rectified linear units as activations, so it works fine. Okay, and also the second question, what is the computational cost of backpropagation? So this is the backward pass with respect to the forward pass. If you have like, I don't know, a rough estimation of what do you think it's the cost, the computational cost. So this will be, for example, the difference between training or just doing inference with the model. And also try to explain why. Okay, I see an answer, but I would also like to see her motivation. Yeah, Mihai, perhaps you can express it in times of the number of forward steps. Yeah, I think it's more than the number of layers and the number of weights. So the backward pass. Okay, I'm still waiting for a complete answer for the second question. And yeah, I'm going to wait, I don't know, 2 or 3 more minutes, perhaps, until to get. Okay, so I'm getting these answers, but I'm trying to just to figure out the complexity with respect to the to the forward pass. So what's the complexity with respect to the forward pass? So what's yeah, the complexity of the backward pass with respect to the forward pass. So essentially, I think these are Mihai, your definition, and also yeah, it could be also the number of layers times number of weights. Okay, so as I said before, yeah, it's twice the forward, but I'm looking for a motivation. So I'm expecting a motivation from either Alexandra or Mihai. Okay, so I'll try to give the answer. So essentially you need to compute the gradients with respect to the input and also with respect to the parameters. So it's about going back to this slide. So in the forward, sorry, this one. So in here we have just to make some operation, we multiply the weights with x and obtain the output. But when we go backwards, we take this gradient, we apply the chain rule with respect to w, and then we also apply the chain rule with respect to x. So we have twice the number of computations. So this is twice. So I will consider your answer as a half right answer. Okay, and I think yeah, these are the two questions. Okay, so yeah, this is the last slide from my lecture. So I'm not sure why. Perhaps I did something wrong with the animation. I didn't see this on the slide. Click. Okay, so yeah, something is wrong with the animation, but I'm not sure. So either way, yeah, this explains once more what happens to the forward, and backward. So essentially, for the backward, usually compute twice the computation. Okay, so yeah, this is the last slide. If you guys have any questions, just let me know. I can stay for a few more minutes. So I'll also go back to the presentation. Perhaps I'll try to fix it. I'm not sure what's wrong with it. Yeah, no, it works okay. Okay, so let's see questions. In Keras, is the mini batch described in this lesson equivalent with the batch size parameter of the fit function. I think so. Let me try to check for that. I think I have some code somewhere in Keras that I used some time ago. Actually, I don't have it. Maybe I don't have it locally. I have it on a different machine. And I cannot check right now, but I think so. Yeah, so I think that's correct. That the batch size is the mini batch that we're talking about here. So usually in practice, when you optimize the mini batch size, you want to, so for example, if you use batch normalization, you would want to use larger mini batches, because batch normalization estimates some norm based on the examples in the mini batch, and if you have small mini batches, you will get worse approximations, and sometimes you will also have problems applying the model. So ideally you want to use larger mini batches. Yeah, but in practice, I don't know, it also depends on the memory that you have on the GPU. So if your GPU doesn't have, I don't know, more than 4 GB of RAM, you can make sure that the model is still able to train by using smaller mini batches. So you can also use, for example, very large models that are also trained on only one example. So the mini batch has one example. Yeah, it's equivalent. So the activation function or transfer function is the same thing. So it's the same concept. So it's also called transfer function or activation function. Okay. Is there any difference between how many samples we send to the GPU and batch we use to compute gradients? Yeah, that's the batch that you use to compute the gradients. So that's the same thing. Yeah, so the mini batch is the number of examples that are used to train the model, are sent to the GPU in a batch. So essentially, when you send the examples to the GPU performs the forward pass and backward pass and computes the gradients on the entire mini batch. Yes, the function is mathematically proven. I can probably point you to, I think I have the physical book somewhere in my office that contains this proof. I don't remember the title exactly, but I think it's one of the books that I recommended for last year in practical machine learning. But I have to double check. So it's definitely proven. The mathematical proof is not very nice to read, but yeah, it is proven. Is there any method to tune the mini batch size? Well, actually, there is some paper by Joshua Bengio regarding the mini batch size. I think I cited it in some paper. So let me see if I can find it here. So there is, there are some interesting results. Let me see if I find the paper here or not. Yeah, I think this is the paper. Oh yeah, so about it seems that the mini batch size and the learning rate are correlated. So if you use larger mini batches, you also can use slightly larger learning rates. If you use smaller mini batches, you have to adjust the learning rate. But in the end, I think you can obtain about the same performance, but the main idea is that to make sure that you tune the number of mini batches um, and the learning rate in the same time. So let me just search for this paper. Actually, I want to find a free version. Well, okay, so I'll have to look for this paper because from the university we have free access and we can obtain it. I'm not sure if I have it somewhere on my machine or not, but yeah, perhaps I can just point you. Let me see if this one is. No, it doesn't have a PDF, or maybe it has. Oops. This one. Yeah, so this is the paper. So yeah, you can let me see. Yeah, they have some graphs here and they show some results with different learning rates and different batch size. So essentially I think the top model, you can use a larger learning rate and a larger batch size, so you obtain this result. If you're using let me see, so you see that, for example, the blue line here, it's almost the same, and here you have a smaller batch size and a smaller learning rate. So these two have to be proportional. So in the end, for example, you can fix the mini batch size, for example, or fix the learning rate and try to find the right mini batch size for your learning rate, or you can try to optimize them together using grid search. I don't know. So, but essentially they should be proportional, and I think the same happens here. So here you have a smaller learning rate and a small batch size. Here you have a larger learning rate and a larger batch size. So I think actually in this paper they claim that if you use larger mini batches and slightly larger learning rates, you can obtain better accuracy. But either way, you have to optimize this together. And yeah, this is also problematic. So the batch size is also depends on the batch size. Also the size of the mini batch also depends on how you tune it with the learning rate. So yeah, I'm posting this. I cannot post it. Well, why? Well, it seems that I cannot post links here. Yeah, I'm trying to. Maybe I can post the title of the paper, and you look for this page and can download the paper and read it. I think this is a good option. Sorry, I cannot post the link, but you can, if you copy paste the title on Google and search for it, you will find this link and can download it from here. Okay, yeah, so are there any other questions? So that's an answer for Catalin, this paper. If you're interested, you can read more on the paper. yeah, that's the conclusion that I mentioned before. To thank you, Maite, for pointing it out. Okay, guys. So thank you for participating. What about what about what? So I'm not sure what I don't understand the question. So you mean what about tweaking the if it's mathematically proven? Um, yeah, there is also some proof on this, but this is a more recent result. Um, and it's actually, I think it was proven after deep learning became a big deal. So I think the proof is in some paper in 2016. And actually, I'm not sure if I saw a mathematical proof or just an empirical proof of it. But right now, yeah, I don't remember the paper, the title of the paper. But I can probably try to look for it and share it with you. So yeah. Yeah, right now I'm sorry, I don't recall the title, but it's definitely addressed and proven at least empirically. They might also have an actual proof. If I remember correctly, they had a proof. But I have to check for the paper. I don't remember the title right now. Okay, so I hope you don't have any other questions. So yeah, thank you for participating. Next time I think we're going to discuss about transfer learning, if I remember correctly. Deep learning. Sorry, it's about convolutional neural networks, and the fourth lecture is about transfer learning and so on. Okay, so we end the lecture here and see you next week at the same time. Thank you for participating.